Hello everyone, welcome to the AI Spotlight series. We are joined today by Tobias Pfaff from DeepMind, who will be speaking about his team's recent paper called Learning to Simulate Complex Physics with Graph Networks. Prior to joining DeepMind, Tobias worked on fracture and thin shell mechanics at UC Berkeley as a postdoc, and worked on turbulent fluid simulations for graphics at ETH Zurich as a PhD student. So, without further ado, give the floor to Tobias.
Hi, everyone, and thank you for the introduction, Karim. And yeah, I'm going to talk to you a little bit about my new work on learning physics using deep networks. And this is shared work with Alvaro Sanchez, Jonathan Goodwin, and Peter Battaglia, who are also at DeepMind, and Rex Ying, who used to be an intern with us, and he's now back at Stanford University, and his advisor, Juro Daskovic. So, and because this is a paper on learning physics, we have a lot of cool videos, but they may or may not show very well over Google Hangouts. So I encourage you to check out our video site. I have a link here and also on the last slide of this presentation on the bottom corner. And you can kind of see there's like a little teaser video of a few minutes, which has our main results. So you can kind of go watch that for yourself if you're really interested in that. All right, let's get this started. Before I actually go into our method and what we did in this paper, let me try to convince you like why we're doing what we're doing. Because this is a question I get a lot about this work. It's like, well, why do you work on predicting simulations, particularly in ML? That's not necessarily something that's like very obvious. Seems like a very specific thing. And at DeepMind, people ask like, okay, well, what's the relation for that to RL? Since that's kind of obviously what we're doing. And so my angle on this is like, actually, simulation is a lot of where scientific compute is in general. So for example, you can look at a Wikipedia page, say like, okay, well, the biggest supercomputer in the world, what does it actually do, right? So that's the Oak Ridge computer. You can get a list of the project it does, and they're all simulation projects. So these are very different types of simulations, of course, than the ones we're looking at in this paper, but they're all simulations, right? And then even further, you can just keep scrolling down and looking at, okay, well, the top 10 supercomputers, like what are they for? And it's almost all simulations. So out of these 10, 9 of them are built for simulation projects. And funny enough, the one that isn't is built for deep learning. So I think the idea is like if you can actually make a dent in some of that insane compute budget or like in these results with machine learning techniques, that would actually be a huge deal. And this is kind of like what motivated me to try to work in that area. And the question is like, okay, well, simulation is, of course, a big and important field for a lot of the sciences and a lot of engineering. When something computational is involved, generally there's a simulation somewhere. But like why learn them necessarily? Because we have all of these simulators, right? And that's also only partially true because there is, of course, a lot of great simulators, and that's kind of what the backbone of a lot of scientific fields is, but they are often very specialized. So you can maybe simulate fracture, right? But like doesn't mean that the type of fracture you simulate the material, the loading scenario, whatever, you can simulate with one of these simulators, right? They may be built for something slightly different and you might need to adapt them. And this is very complex. So there's a lot of grad student years in building these simulators. And of course, they run on supercomputers simply because they are often very expensive to run, especially for large domains. And then there's also some domains where we don't really know exactly what model works. So for example, if you think about climate simulations, which are of course very important, but we only understand like the radiative transfer to a certain degree, like which reflectance, what part of like soil has and all that stuff. There's of course heuristics for that, but you don't know the actual model. And finally, we often want to solve inverse problems, not forward problems with these simulations, right? So if you think about like all these wind tunnel experiments and the simulations, which kind of do the same thing, the idea is you want to find like a kind of a shape of a car or something that like has the least resistance to wind. And you can do that with forward simulations, but it can sometimes be clunky. And I think using learn simulators, you can actually theoretically make a big dent in some of these areas, and I think they can be hugely beneficial if done right. And the area of work I'm in kind of tries to do that, right? So like theoretically, if you have a very general purpose learnable simulation structure, we can reuse that and we can like simulate all sorts of stuff, right? It can be as accurate as the data you throw in, even if you don't really understand the exact model. Or maybe you don't want to model it, right? Maybe that's just like something you just want to fit. You're not really interested in that, but you still want to get the results, right? We can be optimizing them for efficiency, depending on what that means. And I can talk a bit more about that later. And also, these things are often very natural if you want to solve inverse problems, because most learned methods give you gradients for free, and then you can use your like gradient descent methods or whatever directly optimize the thing you want to optimize, right? And so finally, note before actually going to our method, interpretability. Yes, of course, if you learn a simulator, it's not necessarily interpretable, but doesn't mean that necessarily it can't be a first step towards that. And there's some really cool work that's starting to come out now. For example, the one I put a link on here, on how to actually, once you have learned a model of some phenomena, you can use that to regress out some more understandable symbolic rules, right? And I think this is a cool line of work, and I hope to see more of that in this area soon. All right, so what do you actually do? I think if you think about like classical results and like how to simulate physics with learnable methods, then you often think about methods like interaction networks. I'm actually going to highlight how that works because it's very similar to how our method works, and so I can talk about related and our current method at time here. So what they did in 2016, so a while ago, is expressing your physical system you want to simulate as a graph. Right? So you have like a system with particles or rigid bodies, or otherwise objects, and you represent them as nodes in a graph, right? So then you have also edges, and these are like the interactions between these nodes, right? So for example, that can be something like forces that are interchanged between rigid bodies, right? And the way it works is you learn an edge function. So the edge function is kind of the interaction between these nodes. So you can now see what it looks like. You have like a function approximator. You take an edge feature in, and you also take the features and the nodes at the end of these edges in, and you compute some sort of like embedding vector, right? And you do that for all of your edges. And that can be something like, okay, what gravitational force do these objects affect on each other, right? And then once you have that, you can aggregate it. So you can look at every node and just get the edge embedding that you have from the edge function and just sum it up for all of the edges that are like ending in this node. So these two edges here in this case. And then finally, you have a node function, which is, again, some sort of function block that takes in this aggregated edges that end in this node and some node features, whatever they might be. And note that while there's like some interpretation of like, okay, edge functions kind of probably does something like force computation, node function probably does something like forward integration, there's nothing specific that like forces it to have that interpretation, right? Other than your loss at the end, which says like, okay, well, maybe my positions need to be like where they are supposed to be based on my ground truth data. And with that, you can actually simulate quite a few different systems. So like back in the day, they simulated like these kind of systems. You have gravitational dynamics, you can have rigid collisions, and you also can have like kind of these stringy, ropey things, which you can also all simulate with this kind of same type of architecture without necessarily telling it in advance. That's what you're doing, right? It just learns that. And of course, there's, in the meantime, there's been like a lot of more fancy work with very similar methods. So for example, this is a paper which extends the notion of interaction nets to graph nets, which is just like you build these like building blocks out of the same idea that I just described. And you use that to, for example, simulate all of the tasks in this classical MoJoCo control suite. You can kind of get a model for these dynamics and use that for planning or for whatever. But really, these are often very small domains. So like a lot of papers we see on like learning physics with graph nets or related methods are like they're using like tens of bodies and maybe 100 timesteps. And really, kind of the pitch I made to you earlier was about, well, we want to solve these like really big problems in computational science with that. So like things like molecular dynamics, turbulence, or like astrophysics simulation. And these are like operate on like extremely massive time scales. That's and also like spatial scales. That's why they're so expensive, right? So this is like a far cry from the tens of bodies we can simulate with these graph nets. I mean, this is also something, a commonly shared sentiment, like graph nets are like really nice, but they don't scale, right? And so in this work, we kind of want to make a case that actually, I mean, we can actually scale graph nets a lot. So maybe not to this universe level scale that I just showed you, where we ultimately want to go to, but like magnitudes above what we normally look at if we think about like graph net simulations. And so as an example, we show like this type of system, which is like these materials, water, sand, goop, and much more. But I think like the methodology that we're trying to do is like also something that's a bit more broad than this. And we go from tens of steps to up to like tens of thousands of steps. And we also try to show that this kind of system generalizes very well. Okay, so how does our method really work? So again, we start by interpreting our system as a graph. So first we have like our physical system. For example, here is like this block of water, and we use a particle representation. So we represent this block of water made out of a lot of particles. And what we want to do is we want to learn a simulator as theta, which computes the next step in sequence, right? So we have our current step of simulation, right? And we want to produce the next step in sequence and have a loss on that. And the simulation as theta is composed of this dynamics module D and an updater. And dynamics module D is like where all the learned dynamics happen in. So we have this encoder, processor, and a decoder. And the encoder takes the particles that represent our state and encodes it into a graph, right? So what that means for us is each particle is a node in the graph, very similar to these interaction networks I just showed you. And then the edges we simply get by connecting all neighbor nodes. So that means for each node, we look at a certain radius around this node, and all other particles are in that radius are connected with an edge. So we get a locally connected graph. So now that we have this graph, we feed it into GraphNet blocks. That's the processor. And these GraphNet blocks are really just interaction networks. So what we have here is we have like a message passing step. So that's computing these edge and node functions. Then we have a residual connection. Then it gets fed to the next GraphNet block, and so on. And at the end of this chain, we just decode this graph to particle states. So that's our next step, which we can put a loss on them. And so the idea is we do this for like single steps on a training set. And then at test time, the idea is to just like start with a single state, like your starting state of your simulation, and just run the simulator in iteration for like 1,000 steps. You just like keep applying this dynamics module in the updater. To go a little bit into, yes? Okay, yeah, sure. Yeah, sorry about that. Okay, so so specifically what this architecture looks like is that we have an encoder which constructs a graph out of observable quantities from our particle system. So for example, we have a particle position, each of these particles in space, and it has a velocity. That means the current velocity, and also we give it the 5 previous velocities, and that's something that can infer something more about the particle state. And we also give it a type, and that's important if you want to simulate multiple materials at the same time. And so these are all things that are observable. We don't give any like physical properties of the system at all to our learned module. So we don't encode any friction modules. All of these things are kind of learned from these observable quantities. So now, like I said, the encoder encodes this into a graph, and it just does so using a single MLP. So there's nothing magic about this. And again, the processor, which does the message passing steps, has an edge and node function, and they're also not really any special components. They're also just MLPs. So this is really a really simple architecture. And then in the end, we have a decoder which decodes the particle state, which just takes every particle and from this embedding vector with an MLP again, outputs an interpretable quality. For example, what we do here is we output the acceleration, and then we can feed the acceleration into an updater, and the updater in our case is really just an Euler integrator, right? And you can also think about, well, it doesn't need to be an Euler integrator. There's a lot of work on like like these neural ODEs, for example, where you say like, oh, we can actually use all sorts of integrators which give you more accuracy. And I think we can combine this method with like some arbitrary updaters too. But for our case, we just use a simple forward integrator. All right, so what can we do with this system, right? So what we can do with this system is simulate a lot of different materials. So we have these 3 different materials here, like water, sand, and goop. And we can simulate those in 3D and in 2D. And we can then add obstacles into the mix. So we can have these like weirdly shaped walls. Or we can put ramps in there, or even rigid bodies as this cube on the bottom. Or we can then, like, even in one single model, train different materials and their interactions and kind of model that. Or we can start like applying external forces. We can start shaking the box, right? And this is all the same model and the same hyperparameters to learn all of these kind of different scenes. And actually, we use 3 different simulators to generate this data. So there's really nothing specific. We're making assumptions about like how this data is being generated. We have like an SPH, an NPM, and a PPD simulator. And the model just learns to deal with these different data sources and aggregate them all. So how well do we do compared to ground truth here? And if you look at our paper, there's like a lot of MSE numbers, and they may mean a lot or not so much to you. And so I think it's like actually good to look at actually a slow-mo rollout of a trajectory, ground truth versus prediction to get a bit of a sense. And remember, this is like this is 1,000 time steps, but we've only trained on next step prediction. So let's look at that. All right, so you can kind of see, hopefully you can see, that we're staying pretty close to the ground truth even for these very long rollouts. And this is not necessarily a cherry-picked example. So this is actually pretty true for most of the environments that we looked at. And there's many more examples like that you can check out on our video site. But I think the most important aspect in our experiments
Tobias, we have a quick question. So where does the ground truth come from in these simulations?
Right. So, I mean, we don't learn from experimental data. We take it easy and learn from simulators. So we have these 3 ground truth simulators I mentioned. So these are all particle-based simulators. We have a SPH simulator, which is often used to simulate water, especially in graphics, but also astrophysics and some engineering applications. And then these sand and goop dynamics, these are like from NPM, which is material point methods. That's, again, something that's used a lot for like special effects in movies. And then finally, we have a PBD simulator. That's something you often find in game engines, for example. So if you, I don't know, like make your game with Unity or whatever, like the default engines that you can like get plugins for, that's a PBD solver. Flex, for example, is a typical one.
So essentially, on the big picture, what's the main difference between these mesh-free methods and the graph neural network method that you've been using?
Well, so in a way, I mean, there's different simulators. These are all mesh-free ground truth simulators. You can also think about like, and I think I can go into that a little bit later, into like, okay, well, what actually happens if you have a ground truth mesh? We don't use any ground truth mesh. So we have a GraphNet learnable simulator that just gets connectivity by proximity. So this is kind of like what I was trying to illustrate here. So the way information is exchanged in like a mesh-based simulation is by like having a manual mesh. You see like, okay, well, I have like a 3D mesh and like I have like faces, and information can propagate around this. Here, information propagates through neighboring nodes. So because we have information stored in our particles, and we connect particles with the edges to their neighbors, that means eventually we learn message passing kind of like based on how close particles are to each other.
Okay, thank you.
Sure. Right. So I think like one very important point to talk about when talking about all these learned simulators is generalization. Because if you can only kind of reproduce what you have trained on, that's kind of hard to make the case that it is worth doing, right? So ideally, you want to have like a limited training set that you generate with some like external simulator or maybe ground truth data. And then you want to like do a lot of different things with it, because otherwise, like, why do it at all, right? And so we can show that like our graph message actually generalizes pretty well. And the reason for that is because we only model the interaction of a particle with its neighbors, as I just showed, right? So you can kind of imagine at test time, you can take these learned dynamics, which are very local, and then compose them to something more complex, right? And so what we're going to show here is that we have these like training domains where we have a block of water, and the block size and position is randomized, and we have an obstacle, and it's also randomized, and just like the dynamics of this water block falling down an obstacle. So this is the training set. This is what trained on. It has 2,000 particles and this little small domain. And so what can we, from these learned dynamics at training time, do with this at test time? So first of all, we're going to look at what happens if you try to generalize to like significantly more particles and bigger domains. So here's an example. We take this learned model and apply it on a bigger domain, and we just keep on adding particles until we have like 28,000 particles. And you can already see that the dynamics we get are very different from what we have in the training set. So you can see all these like vortices forming, and none of that is observed at training time. They're just like kind of a more complex combination of like the dynamics you have learned. That's kind of very interesting already. And then you can also say like, well, can we scale it further? And it turns out you can. So you can take this much bigger domain. So this is like 30 times the size of our training domain. And we go up to 85,000 particles. And this is like this weird domain that I just drew up in Illustrator with like random ramps everywhere. And the model seems to cope okay with this. And remember, this is all trained on this little box on the side. So this is very interesting, right? And we can also try to generalize kind of in a different sense. We can look at our training domain here, where we have, again, like falling blocks. This time it's different materials. And we can try to use this learned model as we would use a real simulator. That is, by modifying the boundary conditions. So just to do something that's like very far outside of our training domain. Again, a training domain is these boxes, and we here at test time, that's just like me putting hippos everywhere, like falling sand out of thin air, and like goop hippos and some water. And I think the interesting thing is, like, even for this task, which is very far out of our training distribution, we get results that are pretty close to the ground truth. And then what that means to us is that probably our model has learned something that's kind of representative, at least, of the underlying physics, and we're not just interpolating or overfitting to our training regime. Okay, now let me talk a little bit about like why I think this works, right? So we have run a lot of ablations, and we try to identify like what's the kind of the key ingredients that make it work well. And one thing I want to highlight here is the message passing steps. So one difference from our method to like earlier methods is that we take a lot of message passing steps, and earlier methods just like have like one node function and edge function iteration, or maybe two. And I think it's important to take like way more than classically here, because you get more model capacity. That's kind of like a little bit of a trivial argument. Like these scenes that we're trying to model are much more complex than like 10 bodies rotating around each other. So you need a lot of parameters to fit that behavior. But you could also say like, well, we can just take one fat like MLP and put a lot of model parameters in there. I think the more important reason why we want to have a lot of these like residual GraphNet blocks is because information needs to propagate sufficiently to communicate that. For example, here we have this example where you have these like goop boxes that fall on the floor and get squished. In order to keep this box shape together, like the one side of the box needs to know that the other side of the box is all connected, right? So you need to exchange information during the simulation that that's actually happening. And taking a lot of message passing stacks allows us to propagate our embedding vectors back and forth all over the simulation and communicate information like when objects are still like part of the same thing or when they're like squished. And if you don't do that, you often get things that explode. And connectivity radius, that's the radius where we connect everything with edges. That's kind of has a very similar function, right? So the bigger that is, the more, the faster information can kind of spread from one edge of the simulation to the next one. And both of these parameters are very important. And they also allow a bit of a performance accuracy trade-off, right? So the bigger you make them, like the easier it is to fit complicated behavior, but also, I mean, it makes it more costly, of course. And then the second thing I want to briefly talk about is rollout error noise. So you may be surprised if you've done anything similar in the past that we train on next step prediction and then we roll out for 1,000 time steps. Because often what you get if you do that is something like this image here, right? So what happens here is that you get a little bit of error at each step of your model evaluation. And then because you're rolling it out, you're feeding in kind of your output into the model again and again and again, and the error accumulates, right? And at some point, you're ending in a part of the state space which is not seen in your training data, right? So yeah, the model doesn't know what to do anymore. In this case, like everything just explodes. And this is a very common behavior. You also see it in language models. And if all sequence models really have this problem. And the one surprising thing that we learned is that like if you're careful about how to apply your training noise, then you can actually mitigate a lot of that, right? So we use random walk Gaussian training noise. And what it does is kind of like it broadens the amount of parameter space that your model has seen. So if your model has seen in training some noise corrupted state, it's not as surprised if you feed in an output which may contain some noise during rollout time, right? And so the model ends up being very robust to these long rollouts if you apply the right amount of training noise. And it's a very simple method that turned out to be extremely effective. I think like people try to do much more complex things. Often I think like well-tuned training noise can go a long way. And finally, I think the most important finding here is that a lot of these tests we did didn't actually change performance all that much, right? So this is especially things like, well, do we use 2 layers or 3 layers now MLP? Or like how many neurons do we put in? So once you're above a threshold where you have enough capacity to model the behavior you want to model, it doesn't actually matter that much anymore. And that's really good news because it means that it's probably a model that's not that hard to re-implement. If you get a detail slightly wrong, it doesn't really matter that much, right? And also probably gives us hope that you can apply this to something like a slightly different problem and still get some good performance out of it. And so as my final point, I want to briefly go into generalization again. As I said before, I think generalization is kind of one of the key parts on like why learned simulators can be useful and why are graph nets actually that good at generalization, right? And I think it's a combination of a few things. So for one thing, we apply the same dynamics at every particle, right? So what it means is it's not that like a single simulation frame is your state. It's that a single particle is the state because the node and edge function are all shared. You kind of apply the same dynamics at every particle, right? So it needs to learn a representation and a sort of dynamics that work the same for all particles, no matter where they are in the scene, right? And also we use relative encoding. That means that a particle never observes an absolute position. It only knows where it is in relation to its neighbors. I think together what it does is that it reduces significantly the amount of combinations you have to train. And it also like automatically gives you some sort of symmetry. So for example, you get a translational symmetry by only doing relative encoding. So you never need to worry about like the network observing positions that haven't been observed during training because you only have to observe the relative coordinates, right? And the second thing, which I think is like a little bit more subtle, is it does actually give you kind of more effective training data because it's not that like one sample is a frame, one sample is a particle, and you have like maybe thousands of particles per frame. And so you get much more training data per like network evaluation than if you would use just like maybe like a CNN block to predict the whole state. And this is something we're seeing more and more also with other approaches. For example, the NERV paper that just came out, which I'm a really big fan of. They do something very similar, right? They say like, well, not an image is a sample, but like a pixel or like the ray cast through this pixel is a sample. They get a lot of efficiency by like pointing it, by reframing the problem in this way. And I think this is something I would like to see more of because in a way, that's like a very easy way to give you more generalization capabilities and make your models much less likely to overfit, especially if you're considering like out of distribution examples. And then finally, I want to mention a little bit of related work in the area. And I think there's a bunch of papers that are going in the same direction. And if you look in our paper, we run some baselines and have some comparisons to those. But I think like the main difference I want to highlight that what we are trying to do in our paper and what other papers in this field are trying to do is we're trying to provide a framework which is hopefully very general So you can throw in a lot of different physics problems, even though we currently focus on this one specific thing too. So you can have like methods like DPI nets, for example, which is kind of a cool paper, and they show like results on very different materials too. So you can have like a box floating in water. But in order to do that, you need to like kind of manually impose like constraints. So they need to tell this box, okay, a rigid means that like all the particles have a fixed relationship to each other, and they encode that as a rigid constraint, which makes a lot of sense. But in a way, you don't know that for a lot of materials, right? And then like if you can have methods like convnets, which continuous convolutions, which have some strong bias towards liquids, which is mostly what they do. And they work extremely well on liquids. They get some really beautiful results. It's a cool paper. But it doesn't really work that well on things that are not liquids, because a lot of these biases they put in kind of work against you once you go to different materials. So what we're trying to do is like, we really want to pick up material behavior from data. So we only tell it these two are two different materials, and we put in some very general symmetries. And from that, you're supposed to pick up, okay, well, you need to learn that like these yellow particles stay together, versus other thing is like a fluid-like material needs to move around a lot, right? And this is what we're trying to go for in this paper. There's a bunch of limitations. I said we can learn arbitrary particles. It's not strictly true. Like elastics, things like jiggle around a lot are a bit problematic. There's reasons for that I can go into if you want. We are not actually that fast, right? Inference time is the same like order of magnitude than the ground truth simulator. And that's not something we spend a lot of effort on doing. And I think there's a lot of opportunities to make it faster. But for now, we mostly focused on accuracy and generality, and not necessarily on making this faster. And finally, this is a model that works from states. That means you get particle states in and get particle states out. So it doesn't really automatically work from images, which also something that a lot of people want to do. And I think it would be really cool to work on some of these points, right? I think it would be cool to work on elastics more, and especially things like FAM-based elastics, where we have a connectivity already, and see how we can actually leverage that, right? And I think it would also be cool to see, like, well, if you can take larger time steps, larger like spatial resolution, and kind of learn correction models for that to get around the fact that we're not actually that faster than ground truth simulations currently. And just seeing how much we can kind of scale this stuff up would be really cool. Yeah, I think that's the end of my little talk here. And I think what I'm trying to tell you about is like this method, which can be seen as like a high-quality general-purpose learned simulator, and has a much stronger generalization capabilities than a lot of other approaches. And I think like what I hope is that this method, or like a lot of related methods, will kind of start opening up the door to high-performance applications in science and engineering, right? So like this is much more complex than like a lot of these earlier results that we have seen in the area for end-to-end learned simulations. But it's still, I mean, it's not at a stage where it's like really useful directly for an application, probably. But it's really getting close. And I think probably very soon we will actually be able to like get results which are like on par with like really high-quality simulators. And that's something very exciting. And again, here's the links to our paper and the videos. Go see and watch them. Thank you.
Thank you very much, Tobias. Thanks for the talk. It was very, very interesting. We have a few questions from the listeners here.
Sure.
I'll start with the most technical one, and then we go to general overview and discussion points. So one listener mentioned that all the target and all the input and target vectors are normalized element-wise to 0 and unit variance in the manuscript. And doesn't that change the direction of velocity acceleration vectors if different components are scaled differently? Is that true?
I see. Yeah. So I mean, this is something that's kind of more like a model internal step. So we don't necessarily normalize our inputs, right? So like we generate a data set, and the data set has actually like the real physical dimensions, right? And then we have we feed that in our GraphNet models, and after the encoder step, that's when we apply normalization. Okay. That means just like the network input gets a normalized vector, and the network output also gets normalized. But that means that network can actually kind of try to account for that, right? So because the normalization and the denormalization is kind of coupled, it's just really just like intermediate representations. We just like kind of scale it down to like 0 mean and then scale it up back to the normal vector. And then the network learns these scaling factors, so you can totally adapt to that. And we actually tried around with different ways of doing these normalizations. It doesn't actually matter too much. It's one of these things where, like, as long as you don't do something very stupid, it doesn't really matter how exactly you do that. You can also do it without normalization. But I mean, this is like a thing that makes training a little bit easier, because then you don't have to deal with the network initially, kind of like going against your value bounds and all that stuff.
So another interesting question would be, in physical simulators, they might have some time step restrictions, like the CFL number for fluid, for example. So do you notice this time step requirement restriction on your method as well?
This is actually a pretty good question. We haven't done super extensive tests on that. So like, especially a time step is something we just took something that gives us reasonably sized like trajectories. And I think we don't necessarily have the same constraints as, for example, CFL conditions for fluids, because they're really kind of tied to how exactly are you computing your solution. So CFL, for example, comes from the way you do an advection. And there's also like, for example, these the simple Lagrangian-based advection methods, which don't necessarily have to obey CFL conditions. It's really just because when you compute derivatives blows up if you go over your CFL condition, right? And I think, so theoretically, I don't think there's...
Just to keep the listeners informed who don't know about the CFL number, it's just a criteria to stop, basically a criterion that has to be respected by the time steps in your simulator so that your simulation does not blow up. Just to keep everyone who doesn't know about the CFL.
Yeah, thanks for that explanation. Yeah, so I think like there's not necessarily the same kind of fundamental limits if you learn the dynamics, because it can learn all sorts of corrections for it. That said, there's like, of course, limits. So you can make your time step larger and larger and larger, and the dynamics becomes really hard to calculate, because in a way you still have to solve the same problem, right? This is kind of a little bit related to what I meant with the propagation of information before, right? So if you have a wave traveling at a certain speed, you need to, at the very least, propagate information in your graph at the same speed. Otherwise, you can't represent this behavior, and then you will just have something that's exploding or like, I don't know, blurs out or something like that, right? So that means you have to either take enough substeps or like enough meshes passing steps or like small enough time steps to make sure that happens, right? And this is kind of some sort of limit there too, right?
I see.
But we haven't experimented very much with that. And I think it would be very interesting, because I think, I mean, fundamentally, we can probably operate on limits which are much higher than classical simulators, right? Because the model will simply learn to somehow cope with that and maybe be less accurate, but more efficient if you're going on much higher time steps and maybe like lower resolutions, right?
Right.
And I think that's, yeah, it would be very interesting to see how that goes, but we haven't really done much testing on that.
I mean, so on a note, another listener has been asking how fast do you expect these simulations to scale up in the future? So this is basically excellent first steps, but maybe 2 or 3 years down the road, where do you see these simulations, the graph neural networks replacing simulations, and which fields in particular?
Right. I mean, I think, okay, so there's like 2 different things, like how fast they will scale up. I mean, this is currently a little bit of a hardware issue. I think the main reasons there, I think even on current hardware, you could scale them up a little bit by just like being a bit smarter about architecture. But I think like the fundamental limit currently is that a lot of deep learning hardware is built like for like grids, like CNNs and stuff like that. And you have to jump through a few hoops to make that stuff train very well. So for example, we run those things on TPUs, right? And it's kind of not easy to make it work well on TPUs. And there's a lot of performance loss doing that. I think if we actually have hardware which a little bit works better for like sparse computation, I mean, it would get a huge performance boost. This is, of course, not something I can know. But I think this is kind of like one kind of very stupid limitation, which I hope that we will, in the next few years, just like by itself, see resolve. And of course, the normal increase in compute. And the second question is like, well, I think these methods, of course, will have trouble initially scaling to like billions of parameters, right? But there's a lot of problems where I think it can actually, even with like, if you scale it up a bit further, if you go to like hundreds of thousands of particles, or like maybe a million, so you can still like, that's maybe good enough for a lot of applications if you then like get a lot of other benefits from it, right? And I think like, for example, inverse methods is something I really see that stuff being very useful for, because it doesn't necessarily need always to have the high-res simulation you need for like galaxy formation. It's but if you have very fast turnaround times on like things like, I don't know, wind channel simulations, I think that could already like give you a lot of benefit in like optimizing designs, for example.
Right. Another question that I have would be regarding your long-range interaction explanation, that you need several message passing steps to get those long-range interaction. So what I thought about is why don't you have just a larger interaction radius to start with, but you don't necessarily sample all the particles in that radius?
Yeah, that's kind of that's a good point. It's also something we've been thinking a little bit about, but we haven't really done. So I mean, yeah, it's like the obvious thing is like if you make the radius bigger, of course you get more edges. Right. And then like this is like one of the main driver performance, right? But then yeah, you don't necessarily need to take all the edges. You can just like sample them, right? So you get kind of a little bit of a far field sample. And I think this is really cool. And it's also a little bit related to what people do with like sparse transformers, right?
Right.
And I don't know. I mean, I think for certain systems it can work really well. But we haven't really done any tests on that. I think that's a cool direction to take this, honestly. I think that's all I can say that.
So another question. So one question I had was, how does the model deal with boundaries? I see these simulations, hitting a boundary and not going through them. So what keeps the particles from going through is that something physical from the integrator, or is that inbuilt in the graph neural network somewhere?
Yeah, so there's two different things. So you can kind of see on these little boxes on the side. So if you have these ramps, these like little black ramps. So this is actually what I meant with like, we don't really impose very much on our simulator. So these are just particles. So it's just like these ramps are sampled with particles. And the only thing we do with these particles, if they're an obstacle, we just don't move them, right? But everything else is just like learned the same way you learn other materials. It's just like, it has a particle type that's different from the other particle types. The simulator learns, okay, well, these things you can't move through. So you have to like stay on top. And that seems to work pretty well. The only thing is like, we don't use this for domain boundaries because it's also a bit costly, right? Because you get a lot of additional particles, a lot of additional edges. And that's for something like a regular box, that's not even necessary. So like these boxes, both in 3D and 2D, like the domain boundaries, we just give additional features to the network. So the features work the same way as a particle, right? Kind of you say like, okay, what's your distance to these 6 walls we have, right?
Oh, I see.
They're clamped at this particle radius. So you can kind of see like, okay, when I'm going close to a wall, I have like a feature which tells me my distance, right? And this is kind of, can see like the same way you can say like, okay, am I getting close to a different particle, right? And works the same way. It's just a bit more efficient to represent that because especially with regular domain boundaries. But you can also sample the whole boundary with these like black boundary particles and just learn the dynamics. It's just a bit more inefficient.
So are you aware of the possibility of using this in molecular dynamic simulations, in particular? Something similar, but I don't know about this, but listener is asking MPN-based force fields for molecular dynamics.
Yeah, I don't really have very much of a background on that, so I don't necessarily know. I mean, I think graph nets have been used for molecular simulation, so I mean, there may be some connection there, but I'm not necessarily sure what's the thing that makes molecular simulations very hard. I mean, apart from the fact that I guess like it's the time scales a bit insane there, right? So yeah. But yeah, I mean, it's like, this is kind of a little bit why I pick these simulations, because I know how graphic simulations work. So I don't think there's like that many fundamental assumptions like about the stuff we do. I mean, this is really just the simulators we have. But there may be things that make it hard to work on molecular simulations. I mean, they're considered to be one of the hardest things to simulate. I know that, but I don't know necessarily like what are the things to make it hard.
So coming now, I have a few questions regarding grid methods. So not mesh-free methods, but mesh methods.
Yep.
So one question would be like, what's the main benefit that you see with applying it to FEM? Maybe wouldn't it just be the same cost as a normal FEM simulator, or what would be the speed up in applying it to mesh methods?
Right. I mean, so like I hinted a little bit. Like, I mean, I think you can use this on like a grid that you would use in an FEM simulation too, right? I mean, be that a regular grid or even like an irregular grid that you get from some sort of mesh generator, right? And then what you would do is really just say, like, instead of connecting particles based on proximity, you just take the edges from your FEM mesh, right, and then propagate information like this.
Right.
And I think that the benefit, in terms of the benefits, like I think there's like a bunch of things you can get better at compared to hard-coded simulators. And I don't think it's actually that specific to FEM. I think you can make the same point about these methods versus the ground truth SPH simulators, for example, right? We are not currently faster, although we theoretically could be. But it's not necessarily the only benefit you get, right? So like I said initially, so I think one benefit you can get over these simulators is that A, you get gradients for free. B, you get you can actually train on data that's not from a ground truth simulator. You can actually start using that with real simulated data. And I think especially graph nets work really well in that context because real data is very expensive and graph nets are very efficient. So you need like much less data compared to if you just like show like a UNet or like some sort of convnet on this thing, right?
Right.
And I think finally, the other interesting thing that like I kind of feel like I want to explore a little bit more is, well, you don't need to necessarily operate at the same resolutions as your simulator, and you can get much cheaper by doing that. So, for example, if you think about like fluid dynamics, right? The reason you want to have these really big, expensive simulators is because a lot of not because you're really interested in this little worlds that forming, right, but because it's really hard to correctly approximate your like dynamics without doing these little scales, right? But then, I mean, people can simulate them on coarser scales and be much faster. You lose a little bit of this, right, of these details. And if you have a learned model, you can compensate for that, right? So you can be faster by being like, I don't know, taking bigger time steps, taking coarser grids, and then learning kind of like your subgrid model along the way, right? And I think this is kind of, if you really want to get methods that are more efficient than traditional simulators, I think this is probably the way to go.
Right. Another thing about engineering applications, you see, in the middle column there, sand or whatever fluid dropping onto that black boundary. So I was wondering, can you calculate forces out of that? And if you can calculate forces, you can probably have some of this work applied to engineering applications.
Right.
Like
I mean, yeah.
drag
so
around
I
the
think,
car, for example, or an airplane.
Right. Yeah.
Yeah.
So I mean, this is, I mean, in our method, that's pretty straightforward. I mean, we get accelerations out for each particle. You can also have it output forces directly, and then just like instead of like manually getting your like acceleration update, you can just like throw that into kind of like an integrator which just updates your position and velocities based on the forces your model predicts. I think that would work equally well, and then you can also use these forces for all sorts of other things, right?
Right.
I think it's kind of a little bit, it depends very much what you want to do with this thing, right? I think like the bigger question I have for like using this in engineering application is like, what's actually the thing you want to train on, and what's the thing you want to apply it to? Like, what do you want to generalize over? And this is like, for graphics, this is, for me at least, it's a little bit obvious, right? So you want to train on a simple scenario, and then you want to like, it's really important that it can just like apply to all sort of boundary conditions. Like an animator wants to draw a thing and it needs to work there if you want to use this learned model as a real simulator. In engineering, that might be not the case, depending what you do, right? Like if you study like, I don't know, turbulence in like a pipe flow or whatever, you don't necessarily want to start drawing hippos in there, right? But like you probably want to have a training set of some stuff that's easy to compute, and you want to generalize to something that's harder or more interesting. And the real question is like, A, what are these domains? What do you want to generalize to? And how can you make sure with your like the inductive bias you put in these systems that you actually do well generalized there, right? And I think this is a very interesting question. And I think this is a little bit the benefit of doing that in something you understand, like graphics for me, or having a domain expert consulting. If you do these things, not necessarily because you want to know, need to know the actual physics that you put in a system, but because you kind of want to put a very general constraint in that helps you solve the problem in a smart way. And for me, that's really hard to do in other fields, but I think I would really be interested to see like how you need to formulate these things that it works well for these typical engineering simulations.
Right. Well, so we're running out of time now, but thanks a lot for this very enlightening talk, and had fun doing all of this stuff. I just want to remind the viewers that you can see a lot more videos in the link in the top bottom right corner of the slide. And yes, thank you, Tobias, and yeah, see you around.
Sure.
Bye-bye.
Yeah, bye-bye.